This work that I was doing, that I was working on last year while I was in Germany, actually. And we had a team of physicists, so of these authors, Julia Liebert and Christian Schilling are physicists in Munich, in Germany. And the rest of us work like in combinatorics. So it's a very nice example of an interplay between different fields. So, and this talk, I'll try to be as elementary as possible, given I know that for most of you, we are getting out of our usual comfort zone. So let me explain the problem. The first relation that I want to point out between polytopes and somehow operators is the following very nice theorem. So we define a polytope is simply a convex whole of finitely many points. So, you know, a polytope can be a square in 2 dimensions, but not a circle, because that will be, is convex, but it will be the convex whole of infinitely many points. In 3D, you will get something like an Egyptian pyramid or a box, or a rectangular box. And in general, we can define it simply as the convex whole of finitely many points. So given any vector, and yeah, this can be any vector, we can take that one vector, which is 1 point, and start permuting all of the entries. So that's the action of the symmetric group, and it does, it simply reorders the entries of the vector. So a priori, we will get d factorial many points, maybe less because the entries may be equal. And we take the convex whole of that, and that is an object. So it's an object that is a polytope. It has like it's like a ball-like thing, but it has like we can talk about the boundary, vertices, and whatnot. And I mentioned this again. I take one vector and all possible permutations of the entries, and then I take convex whole. This is a very classical object combinatorially, but also because of the following theorem.
Federico,
so this is the Schur-Horn theorem.
Do you have this some pictures or something, your drawings that you're saying like to imagine, because you're saying, but it's difficult for me, like you.
Yeah. Okay, let me try to put a picture here. Well, I don't have the picture and I don't have the iPhone here, but the iPad. But let's try to draw something like really.
Don't worry, Federico. You have a lot of time. You can explain it slowly.
Okay. So this is something that will happen. Let's do one example. I also apologize that most of the time my talk is directed to people who already know this, so I should have put some extra stuff. Okay, so for example, what is this thing? What if I take W equals this guy is equal to 1, 2, 3? You know, this is a vector. Oh my God. So this is a vector, and when I spin those numbers, I will get an hexagon, and it will look like this. Right? So if we do something like this, I will start having numbers like, okay, this is the vector 1, 2, 3, okay? And so on, because we will get 6 permutations of this vector. Yeah. And then we take the convex whole. So this will be, for example, something else. So this will be 2. Not all of them are close together, but this is 2, 1, 3, and so on. So we end up having 6 vertices like this. This thing is an hexagon, it's 2-dimensional, even though I'm plotting it in 3D. Why is this? Because, the dimension is not full dimensional. They all live in one space. They all satisfy the equation x plus y plus c, the 3 coordinates are equal to 6, right? So they live in R3, but they are not full dimensional. They all live in an affine subspace. And if you plot these 6 points, you will get an hexagon. Okay, makes some sense?
Yes, thank you.
So it will be something like this, literally an hexagon. And more than that, it's like a regular hexagon. Everything is very symmetric. So it will get like this. And we are taking the convex whole. So when we say convex whole, really, we take all convex combination, which means that we are really also coloring the inside. We also consider all of these points to be part of the object. Okay, so that's an object that's a subset of RD. On the other hand, so this is subset, is compact, is everything. Now this polytope or this object arose a while ago in a very classical theorem by Schur-Horn. So it's called, well, it was formulated by Schur, then proved by Horn, and there are many, many generalizations of this. And it's quite nice. It says, okay, give me the set of all Hermitian matrices. So an Hermitian matrix will be with a lot of complex numbers, so D times D, so it's a square matrix. And let's say that we fix the spectrum. If the matrices are Hermitian, the spectrum have to be real. So let's say that we fix the spectrum to be W. So now the spectrum is not really a vector. So we are just simply ordered it in any way, let's say decreasing. So the spectrum consists of D real numbers, and I can think of this as a vector if I organize the entries in any way. And what's cool is that if I look at the diagonal of all of these matrices, so the set of all possible diagonals, all of these diagonals are real, right? Because an Hermitian matrix is like when you transpose conjugate, get equal to yourself. So that means that in the diagonal, you have real entries. If you look at all possible diagonals that you can get, now these diagonals, they live in R to the D, so D real numbers. The set of all these possible diagonals is exactly this object on top. Is equal to the convex whole or of taking this W, all permutations, and everything that is a convex combination of them. Okay.
So can I make a question? So then you fix one Hermitian matrix. Yes, you order the spectrum of this matrix, and then you form you put it in a vector W, and then you consider, and then you have this equality. What is the diag of this? The
diagonal, the set of all diagonals. So it's not just one Hermitian matrices, but all of them. So this is like a very large set. And for each of them, I take diagonal.
The diagonal,
and of course, the diagonal has to be real.
Yes, yes. Okay, very good.
The diagonal has to be real, and so you get something that is real. And it's a real bunch of vectors in a real space, and you get this nice polytope, a convex whole of, so in the extreme, you get, of course, you can get the W itself, any permutation, because that could be, I mean, that's kind of easy, but the rest that you get are convex combinations of them. And this is a theorem. It's not an easy theorem, by the way, but it's very classical. It was proven 100 years ago. And it's like a nice relation between these operators and this convex geometry. Okay, so now let me go to the next. How do I delete everything? Okay, but that was just like just the beginning. So what I want to get at is the problem on the physical side and the side of operators. And what we are really going to, this is our setup. So let me review all of these terms. We are going to be working with a Hilbert space, but for us, the Hilbert spaces are all going to be finite dimensional. So this is just linear algebra. So what is a Hilbert space? We really mean literally a complex vector space with a sesquilinear product. So basically like an inner product, but you have to take into account the conjugation. And in a Hilbert space, we have Hermitian operators. So we can also consider the set of all Hermitian operators. What is interesting about Hermitian operators is that they themselves form a real vector space. An Hermitian operator is not, they do not form a complex vector space, because if you have an Hermitian operator or Hermitian matrix, and you multiply times I, for example, the complex I is no longer Hermitian, right? But you can multiply by real scalars, and you can add the Hermitian operators to get an Hermitian operator. So if you are just thinking on these Hermitian operators, they form a real vector space, no longer a complex vector space, but a real one. And this real vector space have an inner product, like a positive definite inner product, like a dot product. And in this case, it's very concrete. It can be explained in terms of the operator. So the product between two of these operators or matrices will be simply the trace of their product. Okay, so this become a Euclidean space. And by Euclidean space, we really mean real vector space. We have an inner product that gives you like a way to measure distances, angles, whatever. You have geometry in the classical sense. There is also another group of operators that are important, which are unitary operators. And very importantly, they are not, I mean, they have a different structure. They are a group. So they are a group, and they are a group that act on Hermitian operators by conjugation. So you know that Hermitian operators are close under conjugation by unitary operators. And related to the set that I was talking before, if you fix the spectrum of something and you act by conjugation unitary operators, then as long as everything is Hermitian, you are on the same, the spectrum is fixed. So we could say that this, there is this nice interplay that will play a role later. And among all of these, we are also going to consider a set of Hermitian operators called density operators. So they call it density operators like this is in quantum mechanics. You can think of them as probability density functions. And by definition, they are going to be Hermitian operators that are positive definite. So this is equivalent to saying all of their eigenvalues are non-negative and the trace is equal to 1. Okay, so the trace equal to 1 means that they are non-negative and they add 1, so they behave like probabilities in a way. And okay, this is a convex set in the Hermitian operators. Convex in the sense that they are a real vector space, so we can talk about convexity. And the set of Hermitian operators then has a spectral characterization. So we basically are looking at all operators, Hermitian operators that have eigenvalues between 0 and 1, and they add 1. So eigenvalues are non-negative and they add 1. And this will be a common theme. Instead of classifying operators, we classify their eigenvalues, and sometimes that is enough. So we go from operators to eigenvalues for their, like we talk about their spectrum. So this is the setup. And by the way, everything is finite, so there are no issues with convergence. Okay, so the spaces that we are interested in, they come from physics, but again, they are completely mathematical and they are finite linear algebra. So people think about when I put a 1, it's the number of particles. And in this right now, it doesn't matter what is a particle, but H1, we are simply going to say we parameterize the states of a particle. Basically, I mean, the cartoon that I have in my mind is you have some finite number of positions that you can be, like D boxes. For us, everything is finite dimensional. So we are really talking about C to the D. So there is some ground dimension D. Let's say that the particle can be in D spots. This is a cartoon, and it's not very important to be rigorous. It's not rigorous. I'm just saying, let's take one particle and that we assign a Hilbert space that we call H1, one to remember that we have one particle. So in this context, people in quantum mechanics, you consider Hn. So now what happens if you have n particles? And this is where things matter if they are bosons or fermions. So in this case, this will be a space of n fermions, meaning they are two things. Indistinguishable. So now you have some sort of symmetric property, but not just indistinguishable, but antisymmetric. And this forces you to consider the exterior product, the wedge product, n times C to the D, which is again a finite vector space. And the idea is we are thinking of these factors as being indistinguishable and antisymmetric. Okay, here mathematically you can do a lot of things. If they are indistinguishable but symmetric, you will take the symmetric product, and mathematically you can take any combination of symmetric and antisymmetric and have something that people in algebra call a Young functor. So I mean, there are many ways of having this C to the D and doing things with them, but we are going to focus completely on the wedge product n times of C D. So these are the two spaces that we have, like we think of one particle and n particles. And for real life, this should be infinite. Like you should have, like the particle have many possibilities of infinitely many states. But we are going to compute everything with finite dimension. But keep it in mind that in order for this to be useful, we need to be able to take the limit. We need to be able to extrapolate. So somehow all of our results, in order for them to be useful, we need to be able to send D to infinity in a stable way. So it needs to not depend on D too much. If whatever we do depend too heavily on D, it will be hard to scale. So we need to be able to go from D equals 10 to 1,000 to 1 million, and then kind of see the pattern and something should stabilize. But everything is going to be finite dimensional. Okay, So there is something that is very important here called the partial trace, and this is something very general. We can say that if you have two Hilbert spaces, we can consider the tensor product, and in the tensor product, we can consider linear maps. So there is a way to have a linear map on the tensor product, and people call this trace out W. We can pass from an operator in a tensor product to an operator on one of the factors simply by literally in the generators taking the trace on the second factor. In this way, we can create a partial trace from the symmetric, from the tensor product to each of the factors. And this, okay, and the problems here, they are similar to probability. Now I can have two, given an operator that is in a tensor product, I have two partial traces. I can trace out W and I can trace out V. So I will get two marginals or partial traces. And the typical kind of question is, okay, given that you only know the traces, can you reconstruct them? Is it true that if I give you two of these operators, are they the partial trace of a single operator? And in my head as a combinatorialist, this is like finite probability. If you have the marginals of a joint distribution, can you reconstruct the joint distribution? I want to say that algebraically, I'm sweeping something under the rug because this is how to get from a tensor product to a factor. We do not have a tensor product. We have something else, but we can adapt the definition of partial trace to this. So this is not a pure tensor product. This is a wedge product, but this can be modified a little bit, and we can talk about partial traces. So this is the map that we are looking at. We have operators here in Hn, and we are going to reduce them. People call the reduction or the marginal or the partial trace. We have an operator on n particles, basically an operation on a very large tensor space, a wedge product, and we can have one of the marginals. Now, technically, you have n marginals, but because everything is symmetric, it suffices to consider one marginal. So I have an operator in the wedge product of n copies of H1, and I want to have an operator there and reduce it to be an operator simply on H1. That's called the partial trace, or the marginal, or the reduction, some people will call it. And we would like to study this operation. So I don't want to consider all Hermitian matrices. I mean, this definition makes sense for any matrix because you can take trace of anything, but we're going to restrict ourselves to Hermitian operators and actually to density operators. Remember that density are Hermitian operators that are non-positive definite, so their eigenvalues are bigger or equal than 0 or non-negative, and they add 1. If I take something like that and I take the reduction, the marginal, the partial trace, what do I get? So that's what is the image of this thing. And there are some physical digressions about why you would like to do this. And if you know something about this, we are doing the mathematically simpler case. What people really care about in chemistry, in quantum chemistry, if you go from n particles to 2 particles, because most of the interactions in physics are binary. If you have a system of n planets, gravity and electromagnetism is always a pairwise action. In this case, we are like, this is physically less relevant. We are only looking at just one particle at the time. And this can be relevant in some contexts, not that it matters so much. We are just doing this mathematically is way simpler. If we, instead of tracing out n-1 and going to 1, if we land in 2 particles in a wedge, if we go from a tensor of 1,000 spaces to the tensor of 2 spaces, in this case, it's much harder. So we are just going to send to partial trace to 1 factor. But this is still relevant. Okay. So we want to characterize the marginals. So basically, yeah, that's what we want to do. I want a density operator. I take the partial trace, and what do I get? So it is not hard to see that you get a density operator, but so you get something Hermitian in principle, and this is unitary invariant. So characterizing the image is the same thing as characterizing the eigenvalues, but not everything is possible. So in order for you to be the partial trace of a density operators on this space of n particles, so this Hilbert space, this is the spectral characterization. This will happen if and only if each of the eigenvalues are between 0. This is in some object called the hypersimplex, but I put this thing in plain English. This means that each eigenvalue must be between 0 and 1 over n, and the total sum is equal to 1. And this is the kind of the kind of description that we want, that in that D is sort of hidden. D is important because you will get D eigenvalue. So the sum of these D numbers will have to be 1. But if you hide that, I mean, if you forget about that for a second, you can describe this without referring to D. So again, each eigenvalue has to be between 0 and 1 over n, and depends on the number of particles. Some people renormalize this and say, well, make the total sum equal to 1, multiply everything times n, but the total sum equal to n, I'm sorry. You can multiply everything times n because you came from n particles, and then you are having all of your eigenvalues normalized between 0 and 1. And this is related to the something called the poly-exclusion principle. So this is related to the fact that that's the occupation number has to be between 0 and 1. So two particles cannot be on the same slot in a way. Okay, but mathematically, that's the content. You take a density operator in the Hilbert space of n particles, so a density operators in a wedge product n times of CD. I take the partial trace, basically tracing out all of the factors. I have an operator now on a single CD. What can I say about the eigenvalue? So if my eigenvalues were non-negative and added to 1, in the image, they will add 1 also, but they are non-negative, but they are bounded from above by 1 over n. That's necessary and sufficient. So instead of characterizing operators, we can characterize their spectra, because everything is unitary invariant. So everything is fixed under the action of the unitary group. So basically, if you have one operator with a given spectrum, you have all of the operators with the same spectrum. So this is also what makes it more combinatorial to me, because then everything becomes real. The spectra are real, and we are going to characterize it. Okay, so now becomes a harder question. Okay, we are taking partial trace, we take a big operator and we convert it into a reduced operator. What if I start with a density operator, but I want to specify the spectrum? I want to say, I take any operator whose spectrum is fixed, is given to W. Again, W have to be in order to be a vector, let's order it from the largest to the lowest eigenvalue. If I fix that, what can be the possible reduction or partial trace or marginal? So I know that I begin with a spectrum of W. I'm going to take the partial trace. I get another operator. What is the spectrum of that operator? It has to depend on W. It cannot be just naively like W, because now your spectrum will have less elements. So it somehow depends on W, but we need to know what it is. So this set is more complicated. It's a unitary orbit by definition almost. I'm taking all possible operators with a fixed spectrum. So you can take one and take conjugation by the unitary group, and then you will get all of them. Basically, what I'm saying is that any two operators with the same spectrum will simply differ by conjugating with a unitary matrix. It is also, well, there is more structure here if you're into symplectic geometry. So this is an interesting set, and we are going to take partial trace of all of its members. So now these indices and subindices are confusing, but again, n is to remember that we are in n particles. So now this one is that we go to one particle. So we were going from the wedge product to simply the Hilbert space, the basis Hilbert space. And this n is just to remember that we come from n particles. And we want to have a spectral characterization. So I want to ask is what happened with the spectrum of that. So again, I take some operator and I know that it has certain spectrum. I take the partial trace of that operator. You give me another operator in a smaller space. What is the spectrum? We want to characterize the spectrum of the reduction. And this is solved. This is known actually. So in 2006, Kliashko gave a spectral characterization. And it's complicated. It's super interesting, but the characterization of this, you have to compute. It uses a lot of a lot of like algebraic geometry, and you have to compute cohomology of certain plaque varieties, and it's hard to put into the computer. So it's beautiful mathematically, but it's not very practical at the level of computing it. The important thing, at least to me, is that this is a convex polytope. This is very surprising. Why would the image be convex at all? But it is convex, and it has like finitely many extremal points. So this becomes a convex polytope, which is very hard to describe. But what he was doing from his work, it ended up being giving finitely many inequalities. So you can say, to characterize this spectrum, you are going to satisfy finitely many inequalities, but producing these inequalities is complicated both theoretically and on a practical level. To just put it into the computer is complicated because there are way too many of them, and they depend on D. And because they depend on D in physics, the application, you want this, you want to be, you want your dependence on D to be better understood, or to depend on D as least as possible. This theorem is really, you read the details of how you do this characterization, and it's complicated. So it's complicated, it's very interesting, it's a pyramid. So everything here is like a massive collective work. So he's using some very general results on co-adjoint orbits by Bernstein and Shamar. And in that paper, they rely on previous work by Kliashko, so they fit into each other. But these inequalities that they use and these techniques are later refined by Nicolas Resier. And just the fact that this set is a convex polytope and convexity, it follows from other very general convexity results theorem by Kirwan that was generalizing some work by Guillemin, Stenver, and Constant. And these guys were generalizing the Schurhorn theorem that I mentioned in the first slide. So this is really like a long list of results and theory that build on top of each other. This is a very collective work, and everyone is doing something. I guess even these people here are giving support, even if they are not in the pyramid. Okay, so again, this was complicated. To find exact characterization, we are going to relax it a little bit. And instead of finding all possible spectra, we just want to find something more relaxed, all possible diagonals. And we're going to look at all possible diagonals. And when we look at all possible diagonals, because of the Schurhorn theorem, we are looking at somehow the convex hull of all possible spectra, but now we have to symmetrize something. So what we are doing is relaxing the problem, enlarging the set, and I have this kind of cartoonish thing. The set of all spectra of all possible spectra of the reduced density matrices coming from a W, it has to depend on W, N, and D. This set is something. This is the spectrum. So the spectra ordered from largest to lowest, I can consider them as vectors. And this is the green thing. The green petal is what we want. This is what was described by Kliashko, and this is what is super relevant. To compute the green petal is complicated. So we propose a convex relaxation of this. So instead of focusing on this petal, what we say is take this petal, consider all of the possible rearrangement of coordinates. So we symmetrize the petal. So why do we get 6 petals? Because this is similar to the picture that I was drawing in the first slide. If this was dimension, if you had 3 entries, the symmetrization will look like an hexagon. So we are taking this petal, taking all of the permutations of the coordinates. So we get the yellow flower, but we then of that yellow flower, we take the convex hull of the yellow flower. So when we come and restrict to the space where everything is decreasing, we capture something that is larger than the green petal. Okay, so we are computing the convex hull of the red thing, and we can restrict ourselves to all of the vectors that are decreasing. That will be the blue part, and this thing is larger than the green petal. We would like to capture the green petal, but we cannot do it. So, but we can compute inequalities. So we are doing this blue relaxation with the advantage that we are going to compute this convex body, with concrete inequalities. So our goal is to enlarge this a little bit, but now give inequalities that have to be satisfied. So instead of just saying, oh, all of the eigenvalues have to be between 0 and 1, or 0 and 1 over n, there are other linear inequalities. Maybe the sum of the largest two plus the third largest is bounded by something. And all of these linear inequalities we are going to describe them, and they are going to be necessary but not sufficient, because we are going to be capturing something bigger than the green petal. Okay. And our inequalities are, I mean, they do not depend on D that much. Okay. So this is what we are doing. We take some operators with a fixed spectrum. We take the reduction and take all possible spectrum of that reduction. The spectrum is a set, it's not a vector. So we order the spectrum in all possible ways, give me a very large orbit, and we take the convex hull of that. And that is what we are going to compute. The convex hull of all possible spectra taken in all possible orders. And it will be something like this. It will be some sort of the orange one.
I have one question. This is really one example of the difficulties that you have when you fix the spectrum and you want to recover operators. Just could you go to the previous slide? To the previous slide. Yes, here you mentioned that for this Schur-Horn Revisite theorem, not that one, the next one. Yes. The next one. Here, you mentioned that you use one convexity theorem by Atiyah and Guillem in December.
Yes.
Could you mention some details about this theorem, or which this theorem says?
Yes, this theorem. Okay, this theorem involves words that I have not said here at all. Their point of view is that, okay, when you look at this set, the set of D and W, this set is a unitary orbit. So by definition, you fix the spectrum, so you can take one operator and you let the unitary group act by conjugation. So we are looking at one orbit. Now, because of people here use Lie theory and they say this looks like an adjoint orbit, but not really. People will look at this and call it a co-adjoint orbit of the unitary group.
Yes.
So these co-adjoint orbits in general, they have a lot of structure. They are actually a symplectic manifold, and you can define on them something called a moment map. And what's happening here is that this is the image of a moment map. And it's not clear at all why the image of the moment map will be convex. And this is the theorem that Atiyah, Guillem, and Stenberg were talking about, the moment map. They were looking at the case where you act by a torus, the orbit of a torus. That's kind of, well, the case of the torus is simpler. When you have the action, a torus action, here we have a unitary action, which is non-abelian, which makes things more complicated. This is why I was referring to a more general convexity result by Kirwan. So the key word here that I'm not mentioning is moment map. These general convexity results are on saying that the image of a moment map is convex. And these were some big theorems in the 80s. And that's what guarantees that what we're looking at is convex, which is not clear a priori. So the language that they use is this Lie theoretical. They will look at a co-adjoint orbit and how it decomposes and so on. So if you look at their work, they are talking about moment maps. That's the sauce.
Thank you. Sorry for interrupting you. Only that was I look that interesting because precisely this week I was talking with Santiago, who is interested in the symplectic structure of this co-adjoint orbit. Yeah. So that was the reason because I interrupted you. Yeah. But please continue. Yeah. Thank you for the details.
That's a whole other word. And at the end of the day, for me in combinatorics, we are getting like a polytope. We are getting something that is discrete and finite, with finitely many extremal points. So now we start defining how we are going to describe all possible spectra, all of our set that was the convex hull of all possible spectra, reordered in any way. We are going to describe now polytopes. And this is, now again, this is maybe familiar to some of you, but let me just briefly tell you how all of these things connect. So basically, I have some points and everything now becomes finite. I have finitely many points, not even the convex hull of anything. And we're going to simply define a lineup as being, I throw a linear functional, and to me, a linear functional is simply a direction, and you move like in that direction. And you look at what are the largest values. Larger, you can think of them as the first values that you get. And this R will simply say, well, maybe I don't need to order all of them, not the 6 of them, but let's say that R is equal to 3. So I throw this linear functional pointing to the left in this case, and the largest one is E, the second one will be A, the third one will be B, and then C, D, F. And if I want to specify that it's a 3 lineup, I only care about the 3 largest ones. Some people, I mean, we also call them a podium. When you go to the Olympics, you don't care, you don't rank all of them, you just get 1, 2, 3, or well, at least those are the ones that get medal. And some things are lineups and some things are not. So again, a lineup is just like a possible order. EAB is a possible lineup. FAD is not a possible lineup. So you think about this for a while and you realize there is no way that F is the largest one for a functional, A the second largest one, and D the third largest one. No way. This is where combinatorics will come into play, oriented matrix and whatnot. There is no way that that happens because C will have to be there somehow. You cannot have F, A, and D be the largest ones, implying that C is not in the top 3, but you cannot cover F, A, D without already passing through C. So this is not possible. FAD is not, there is no way, there is no linear functional that has F as the largest one, A as the second largest one, D as the third largest one. So this game can be played for any set of points. And here we use the hypersimplex. So again, what is the hypersimplex? I'm looking at all possible 0, 1 vectors of length 8 with 4 entries equal to 1. This is a finite set, it's 8 choose 4. And I'm going to try to see what are all possible 3 lineups. All possible, I have to choose 3 points in order, and they have to be the result of taking a linear functional maximum, second maximum, and third maximum. And by symmetry, everything is here is symmetric, so I'm going to take a linear functional. In this case, a linear functional is just simply the dot product. So I have 8 entries, and I'm doing dot product versus this linear functional, and I'm going to order them decreasingly by symmetry. By symmetry, everything here will be, I can restrict to this case. So if I have my entries of the linear functional decreasing, and I do the inner product versus all of these points, the largest one will always be 1, 1, 1, 1, 0, 0, 0, 0. And instead of saying the vector, we can simply say the one corresponding to the subset 1, 2, 1, 2, 3, 4. The second largest one, no matter what, is going to be 1, 1, 1, 0, 1, 0, 0, 0. And the subset is 1, 2, 3, 5. And then the third largest one, now it depends. I mean, the fact that these guys are decreasing will imply that the next one could be something like 1, 2, 3, 6 or 1, 2, 4, 5. It's not clear which one it has to be. It depends on what? It depends on a linear condition. Literally, it depends on whether the dot product with this one or the dot product with this one is larger. And the dot product of y with the first one is literally just doing the dot product, give me y1, y2, y3, y6. Oh, there is a typo here. This should be a y6. And the other one is, well, this is completely wrong. This is y1, y2, y3, y6 versus y1, y2, y4, y5. Oh, so this on the right hand is fine. This should be a 6. And when you compare, now there is a split. It depends on whether this is larger than this. So either can happen. And that's kind of it up to symmetry. So up to symmetry, we will get 1 and 2, and then you have to consider all possible cases. But then up to symmetry, you just let the symmetric group act on this. Oh, my time is almost up. Okay, so this is basically we are just recording all possibilities. It's very combinatorial. I got 3 possibilities, but I have to now consider all possible orderings of this guy. So that's something to consider and to keep in mind. And this is where the combinatorics start kicking in. If this thing is decreasing, I know just looking at the subset that 1, 2, 3, 4, this vector will have a larger value, a larger inner product than 1, 2, 1, 2, 4, 5 or 1, 2, 3, 6. As long as I can move, as long as I can replace each of these numbers by something bigger, I know that it will become smaller in this case. So this is where something called the Gale order comes into play. We declare that 1, 2, 3, 4 is larger than 2, 3, 4, 5 because point-wise they are smaller, and something like this will keep happening if I look at all of these possible vectors and all of the possible dot products. They will be ordered following some combinatorial picture like this. I know for a fact that 1, 2, 3, 6 has to be larger than 1, 2, 4, 6, but in some cases there is no relation. 1, 2, 3, 7 and 1, 2, 4, 5. I mean, it could be one or the other one. There is no implied relation. So we can start looking at the lineups by looking at this picture, but we cannot completely combinatorialize this. We still don't know how, and we believe it to be very hard to just look at the subsets and look at this order and say, oh, this is possible or this is impossible. When we start considering more and more elements, there are some restrictions that are geometric and that I cannot capture just looking at the subsets. So this is a mixture between combinatorics and geometry. So we use this, and the main result here, basically just to close this, the main result is that we create another polytope that has a vertex for each possible lineup. So a lineup was an ordering, and this is the recipe. This is the recipe. We have the ordering, and to each ordering we associate a vector by choosing some extra W, and we basically add them with weights, and we create one vertex. So we go from lineups to vertices. That's more or less what we do, and there is a lot of like compatibility with this. So you are optimized in this vertex. This vertex optimize certain linear functional over this new polytope, if and only if the linear functional was inducing the certain lineup on P. So we go from lineups to vertices. That's all I want to say in a way that makes sense. And what's the point? Well, we have some example here. Maybe this is an example that I don't have a lot of time to talk about, but this is an example in which this will correspond to a bosonic configuration at the end of the day in physics, and is that we now allow, previously all of my entries were 0 or 1, like basically the particle is there or not there. Now we're going to consider 3 particles, but they can stack on top of each other. So it could be like 3 on the first coordinate 0, 0, and we consider basically all possible integer vector with, let's say, length 4. So we have like 4 slots, and the sum of them is equal to 3. So let's say that you have 3 particles, and they have to accumulate, but they can accumulate in many ways. It can be 3, 0, 0, 0, or 0, 1, 2, 0, 1, 0, 2, or 0, 1, 1, 1. So these again are vectors, and if I have vectors, I can consider lineups, and these lineups, I have to take all of these possible lineups, let's say 4, so I'm looking at the largest 4, and we run this thing that we were defining before, and is that for each of these 4 lineups, we're going to produce one vertex, and we are going to have one polytope that parameterize all of these lineups. And the details are not too important, but the picture is super important. It will look like this. So now finally, I should put this picture way before. So now we have 3 lineups. Yeah, there were 4 lineups, sorry, in this case, 4 possibilities. And these 4 possibilities, we still had to symmetrize, because there was something that we say, well, we are assuming that everything is decreasing, that the linear functional is decreasing, but by symmetry, we simply let the symmetric group act on this, and we take the convex hull of this thing, and it will look like this. It's a very nice figure that we want to understand better. The important thing about this figure is that polytopes have 2 descriptions. It's either the convex hull of finitely many points, and we can tell you what are these points, or more importantly, the solution set to finitely many inequalities. So what we really want, and the reason why these theorems about something being a convex polytopes are big, is because that implies that there are a finite set of linear inequalities that define the set. So surprisingly simple. In this case, it will look like this. So this set has a lot of inequalities, but with up to symmetry, we can describe just this one. We are looking at all vectors in dimension 4. So this will be the spectrum of something, no? So they have to add 3, and the down arrow means order them decreasingly. So the second line is saying the sum of the largest 3 is at most 3. The largest one is at most 2 plus W1. This depends on some W. And these are the linear conditions. There's 2 times the largest one plus the second largest one has another inequality, and so on. So we can produce this finite, concrete, computable list of inequalities that these guys have to satisfy. Okay, so we can define this polytope and we can produce the inequalities in a concrete way. And that's kind of like the end of this thing, because just to close everything, the convex hull of the spectra of this thing. So remember a while ago we were talking about having operators with a given spectrum. We take the reduced version, the partial traces, those was other operator. We take the spectra. Now we order the spectra in any way, and we take the convex hull. So we have this set consisting of the convex hull of a spectra, and here by a spectra we mean we take the spectrum and order it in all possible ways. That's where the combinatories come into play. We need to consider all of them. And this thing is a lineup polytope for a hypersimplex. And in this example, this was not the hypersimplex, but this will correspond to a bosonic case. So we were always considering the partial trace to come from a wedge product, but you can also do it in a symmetric case. And this is the kind of thing that you will get. I put this example because the smallest examples that I can do in the case that I was talking previously, they are very large dimensional, and I cannot even mention them here. But we can create the spectra. We can classify the spectra. We can throw inequalities for the spectra, and these inequalities for the spectra will look like this. There will be inequalities on the spectra ordered from the largest one to the smallest one. There will be linear inequalities. It's amazing that why linear inequalities are enough, right? Why is not the case that the possible spectrum are described by something quadratic or something, or not even by an algebraic equation, but all of these are linear constraints. We have this linear constraint here, and the right-hand side will depend on W, and that W really is coming from the spectrum, because everything should depend on W somehow. So that's more or less the idea, that we can characterize the convex hull of this spectra in terms of the flower, the big red flower, with a polytope that we can describe combinatorially with a lot of combinatorics, which allow us to compute things. And again, we can compute this very explicitly. We don't have like a general formula. This is too complicated, but with a lot of computational power and some clever algorithms using dynamic programming, Gale orderings, and so on, we managed to produce explicit inequalities for some cases. And this is kind of cool. Well, and these restrictions are very concrete. And now apparently the next stage is to test them in a lab somehow. But that is something that is beyond my. I mean, I cannot talk too much about that, but it's kind of cool to do this kind of mathematics that can be like they are interacting with physics somehow. And that's all I wanted to say. Thank you for coming.
Oh, thank you, Federico. I think it's very interesting talk, very inspiring, of course. So we are open for questions. Probably I can start doing one question, but myself, how did you prove in the previous slide that the independence of this parameter D is very curious?
Yes, good point.
Or is very technical, maybe.
No. I am the truth is that I am cheating a little bit here. Okay, so what we do is that for physical considerations, what we do is that we keep just the lineup of size, let's say 3. We fix the R fix. In physics, this corresponds to something about the energy levels of the configuration. So basically, we look at a fixed number of levels. So we only care about the 20 largest levels, but we don't care about the rest. And the rest, that tail can be as long as possible. So if somehow I only care, all of these things have to be thought of as like some configurations of electrons, something like that. And we are looking at the largest 3 energy levels. If we only care about the largest 3 energy levels and we don't care about the rest, that is where the rest can be 1,000 or 1,000,000, and we don't care. If we only care about the top 3, if you care about the ranking of all of them, then yes, it sort of depends on how many you have. So this dependence on D is has an asterisk. Is saying, suppose you only care about the largest 4 or 5 energy levels somehow, you only care about the top 5 eigenvalues. That's sometimes, and this is something that people do. I mean, I don't know in your work, but in graph theory, people really like the largest eigenvalue.
Yes,
right?
yes.
That seems to control like a lot, or the second one, the eigengap. So people usually, sometimes people only care about the largest 2 eigenvalues. So in this context, if you only care about the largest fixed eigenvalues, then it really doesn't matter how many you have below that. The largest 5, but you have 10 million, it doesn't matter. That's the stability that we're looking for.
Very interesting. Okay. So yes, for us also it's relevant. For example, we take pseudo differential operators and we discretize these operators. So we add. We put these operators acting on vector spaces of finite dimension, and we study the spectrum of these operators. And after that, we check how the spectrum behaves when you increase the dimension, for example. This is one of the numerical issues, for example, that are important. And also a lot of graph theories inside of that technique. So very interesting. Okay. Any other question for Federico?
Yes, I have a question. So at the end, you get inequalities to describe the convex hull of D1, right?
The convex hull of these things, yeah. So we get inequalities for the superflower.
Yeah, but then you can get the inequalities for the petal that the algebraic geometry is given to you, or not?
No. We can get some of them. Like, look at this picture. In this picture, some of them, like there are 2 here that are petal and relaxation, right? Now the relaxation is giving us extra stuff that we don't know, but there are inequalities of the petal that we do not get because how do I mean, you can see the petal can have something here that we will not detect.
But your inequalities are giving you the blue zone or the whole.
Like no. Yeah, our inequalities will give the orange, but to go from the orange to the blue is super easy. So let's say the
easy.
Blue.
And going from the blue to the green one is difficult, or you don't know.
That is too hard, and that is why again, it depends who you are talking to here. Some people will say, "Oh, this looks very weak," but in convex, I mean, when people work in optimization, sometimes really you cannot do it. The best way is to do a convex relaxation and live with that. So yes, the petal is better, but the problem is that people have not been able to compute with that cohomology computations. They are hard to do with a large number of parameters. So we have the advantage of being like less useful but more computable. Like we can. That's the trade-off here. And also we use much less technology, right? As I was mentioning, they are using like really, their tools have been developed for 100 years. But yes, it is true that we cannot recover the green petal. We are relaxing the petal.
Okay. And I ask you, is there any measure that or any way to know if you change the set W for another W set? Is any measure who measures how much like the polytope change?
Yes, I mean, I haven't thought about that, but here the thing can be like, you can think that if W is 1 and a bunch of zeros, this picture will be the full simplex. And as I move W, as I make W more complicated, the picture will get away from the peaks. It will stay away from the and then, but we don't know how to measure this. There was a naive thing saying like, oh, let's measure the volume that you lose. But that is not helpful. I mean, you cannot just use the volume. For some discrete geometry reasons, most of the volume is inside, like most of the volume is, I mean, for some reasons that have nothing to do with physics, most of the volume will be still there. So that's not interesting.
So that's not the information you need.
But we need a measure. Yeah, we need a measure of how far you are from here. Maybe we have to weight harder. Some different measure that maybe is heavier here, and we don't care about it. Like the super interior is like we have to deal with that. And I don't know, but the people in physics are trying to like put some numerical value on how much that matters. It cannot be a naive volume. That's all I can say.
Okay. And then the polytope tries to become what? Do you have like an idea? Like
it becomes, but in the extremal case, I mean, for example, if you keep pushing W, I mean, you will never leave this vertex. This is a good point. This thing and this thing will collide, and at some point they will become one here, but that guy will not disappear. So you will get this. That's why I'm saying that the volume is not going to be helpful, because no matter what, you will never affect this region, but this will become super complicated, the part on top. So these lines will stay, but then the part that is on top will become more and more complicated. Yeah.
Okay, thank you.
Okay, thank you. More questions? If no, so we can say to Federico, thanks for the talk, very interesting talk. So Federico, if you want, you can stop sharing. And we have a tradition in our Methusalem seminar is the tradition of informal questions. Usually Bolis is in charge of these informal questions.
Okay.
So Bolis, you want to proceed, or Vishpesh or David? Maybe Vishwesh, you want?
Okay, if Bolis is not here, it look like, so I will. So first question we generally ask Federico, that what do you consider mathematics? Is it art or is it science for you? Like in your opinion, what are your feeling?
My God, these are such a deep question.
I know it's a philosophical. It's just very formal.
I think it's science, and now working with these things of physics, it's kind of cool how the motivations always, not always, but historically maybe they come a lot from physics and from trial and error. And people think that we don't do trial and error, but we think mathematics is done with trial and error. Maybe not with the scientific method, but we certainly have to, have a hypothesis tested in a way, play with the computer, test something, simulate something, and then you start seeing what's possible. I don't think, or I don't know, I mean, and I don't know, maybe ultra theoretical people sit in an armchair and think what can be true. I don't think so. You have to scratch paper to try to guess what will be true. You have to experiment to try to see what is true. So for me, it's definitely a science in that sense.
Okay, thank you. We have had a lot of answers here. Art, sometimes science, sometimes, again, the past seminar, a guy from USA told us that for him, mathematics is a game. So it was very nice to have you in our seminar. You are welcome always to the Ghent Methusalem seminar. So next seminar will be by the Belgium Park from Korea. We will pass from combinatorics to harmonic analysis again. And the title of the talk of Belgium Park will be is multilinear route singular integrals. So Federico, you are welcome, and thank you to all the participants for connecting. So see you.
Thank you very much for this interesting talk.
That's it.
See you all.